Remember that the number one question that we're asking in this unit is, does the series converge or diverge? And I mentioned earlier that we're learning 10 different tests in order to answer that question. To recap, we've learned the first one was telescoping. The telescoping test can determine whether all of the terms except for a finite number of terms cancels out, and then the series converges to that particular set of values that don't cancel out. We had the geometric series, probably the most important, and that talked about the common ratio and whether it's between -1 and 1. If the common ratio is between -1 and 1, then our series converges. And if it's not, then it doesn't. Pretty straightforward tests for very particular sorts of series. Another fairly straightforward test is the nth term test. Notice that this is the nth term test for divergence. So, in other words, we cannot use the nth term test for convergence. We can only determine that a series diverges using the nth term test. So, how does it work? Well, what we do is we look at the individual terms of the series. So, a sub n, for example, we've got 2 raised to the n. Well, that means a sub n is 2 raised to the n, which is the sequence starting at n equals 0, 1, 2, 4, 8, etc. Now, if we take a look at the limit as n approaches infinity of a sub n, it's pretty clear that 2 to the n is going to infinity. All right? So that means that I'm taking 1 for the sum, for the series here that we're adding up, we're taking 1 plus 2 plus 4 plus 8. These values are approaching infinity. Of course, if the values that we're adding are approaching infinity, then our sum is just going to be growing crazy fast, exponentially fast. So, so this is not equal to 0. Therefore, the series diverges by the nth term test. Okay, that's the only conclusion we can come to using the nth term test. We can never say the nth term test tells us of convergence. All right, so let's take a look at this next one. Maybe we can zoom in so we don't have to squint so much. This next one, let's take a look at a sub n is equal to n factorial over 2n plus 1 factorial. If I take a look at the limit as n approaches infinity of this fraction, I can say, well, let's take a look at large values. For example, 10, right? 10 factorial over 2 times 10 factorial plus 1, right? That plus 1 is fairly insignificant. It's completely insignificant for extremely large values for n. So we can say that this is the same thing as the limit as n approaches infinity of the big stuff, right? The n factorial over 2 times n factorial. And we know that this can cancel out with that, so we don't have any more n's, and we have 1/2. And you can easily play around with values of n, plugging them into a calculator, and you can see that this sequence is going to approach 1/2 probably quite rapidly, because that plus 1 is going to become so insignificant compared to these factorial values that grow quite quickly. All right, so we're adding up values that are close to 1/2 over and over and over again. Okay, but if we take 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2, that sum is growing without bound. There is no limit to how big that sum is going to get. If this term does not approach 0, then we have no chance of the sum converging. So notice on this last example, we got infinity, so we said, oh, well, that diverges. The sequence diverges, therefore the series must diverge. Over here, we can see that the sequence converges. It converges to 1/2, but it doesn't converge to 0. If the sequence, remember the individual terms before we add them up, if the sequence converges to something other than 0, then we're adding something bigger than 0 over and over and over again. Which means that the series, not the sequence, the series diverges by the nth term test. Okay, because we have to get 0 here. All right, so that leads us to, finally, we take a look at this one and we say, oh, well, if we take a look at the limit as n approaches infinity of 1 over n, we get 0. Therefore, we must say it converges, right? Wrong. We can't do that because the nth term test does not tell us anything about converging values. It only tells us about diverging values. So we're going to say, therefore, the nth term test, nth term is inconclusive, which means we still don't know how this simple harmonic series behaves. Maybe it diverges, maybe it converges. It passes that first test for convergence, but that's not enough. This is a prerequisite for all convergent series, but it's not sufficient, right? We need that and then other things as well. So we still don't know about this sum of the reciprocals of consecutive integers. All right, so that's unfortunate, but we'll get there. We're almost there, just not in this section, so be patient. All right, so we will move on to number 12. Take a look at this. We've got a fraction here. We'll take the limit of that fraction as n approaches infinity of this fraction. And we're used to these by now, right? The degree on the top is the same as the degree on the bottom, so we just look at the coefficients. That's equal to 2/3. So the sequence of values converges to 2/3, but 2/3 is not 0. Therefore, the series diverges by the nth term test. So don't get confused here. We're talking about two different things. Remember, the sequence is just the individual terms. And then the series is adding up those individual terms. So the values in the sequence are approaching 2/3. And when we add up a whole bunch of 2/3, it just grows. The sum is going to grow forever and ever and ever. All right, so that's why it diverges. That's the reasoning behind the nth term test. All right, now we look at this next one. We look at the limit as n approaches infinity of 1 over 1.1 to the n. And, well, 1.1 is bigger than 1, so when we raise that to large values, it's going to get bigger. So this is going to be 1 over infinity, which approaches 0. Therefore, what? You guys tell me. The nth term test is? I heard someone say it. Inconclusive. All right. So that doesn't mean that we have an answer for whether this series converges or not. That just means that the nth term test wasn't helpful. All right. So so I liken the nth term test to any sort of limit problem where you say, well, the first thing you try is direct substitution. And if direct substitution works, then you're done in a limit problem, right? But when does the direct substitution process work in the limits? Almost never. When does the nth term test work? Almost never. Almost always when we try to look at a series, we're going to get a limit of 0. But every once in a while, we're going to find non-zero values, and then we can just say, oh, we're done. This thing diverges. But in this case, we have more work to do. We look at this series, and we actually recognize this as a geometric series. So R equals 1 over 1.1. That's what we're multiplying by. And that is, the absolute value of that is less than 1. So this series converges. Not only can we say it converges, we can say it converges to a particular value, to S equals the first term, which is, well, let's rewrite this because 1.1 is 11 over 10. So we can write this as 10 over 11 raised to the n. And if n starts at 2 and goes to infinity, then our first term is 10 squared over 11 squared. Okay, that's our a value over 1 minus our r value, our r value. All right, so that gives us a fraction that we can reduce. This is, the denominator is 1/11th, so we're going to take this divided by 1/11th, which is the same thing as multiplying by 11 over 1, and then the 11s cancel out, we get 100 over 11. So we get that by the geometric series test, not by the nth term test. The nth term test was inconclusive. Finally, we're done because that was the last one. Great.